Hello, AP Calculus students of the future. It's Mr. Ford with another summer packet tutorial. This time we're talking about topic D. And topic D is even and odd functions and symmetry. Now this is a topic that might be probably the one in this packet that is going to be the most new. It's the kind of thing that, honestly, if you don't know it at all, you're probably still going to be fine on the class. But oftentimes, recognizing that a function has symmetry or is even and odd can really help you take shortcuts or think about different problems different ways. So it's worth doing this lesson right now just to get a reminder on what these things are. Before we start, let's review what even and odd functions are. An even function is one that if you have, like, say, f of x, some function going on there, like, I don't know, I'm just going to say f of x. Now let me try this again here from the top. From the start, from the top, got it. All right, an even function is one where if you plug in a negative x into the function, you get back the original function. Another way to say this is that if you were to plug in xy, let's say some point xy exists on the graph, then negative xy also exists on this graph. The side effect of this, the way that makes this really easy to notice, is that it has y-axis symmetry. And even if you graph it really quick, you can see exactly what I'm talking about. If some point xy is on the graph, then negative xy is also on the graph. So a graph that looks maybe something like this would be a good example of an even function. Odd functions, kind of the same idea here. Odd functions are ones for which if you plug in f of negative x, you get negative f of x. In fact, in other words, you get the opposite of the original function. So in other words, if you had some sort of xy pair that satisfies the original equation, then the opposite of both negative x, negative y is on the function also. Now this does not cause y-axis or x-axis symmetry. It causes what is called origin symmetry, sometimes also known as rotational symmetry, which basically says you can take the graph and rotate it 180 degrees around the origin, and it'll map onto itself. We'll take a look at an example right now. I'm sure we'll see a couple examples like this in a minute. But a good example of this is f of x equals x to the third power, which looks like this. But more generally, if, again, some xy pair is on the graph, then negative x, negative y is also on the graph. That's the key. We have some more to add to this in a minute, but let's do number 1 through 6 with this in mind. I'll show you exactly how to do this without a calculator even. So here's the idea. First of all, number 1 is kind of a special case, but it helps us talk about this a little bit. You might already know what the graph of this looks like. It's a horizontal line that goes through 7. 1, 2, 3, 4, 5, 6, 7. Horizontal line right there. This is an even function because it has y-axis symmetry, but it also has y-axis symmetry because it's an even function. Here's the thing. F of negative x in this problem is still 7, since x is not a part of the function at all. F of x is 7, f of negative x is 7, f of any input is 7. So since these are exactly the same, this means that this is an even function. Let's look at number 2. Now, we don't need to graph all these all the time. In fact, what you really want to do to determine if it's even or odd, you just want to plug in negative x and then simplify as much as you can. F of negative x in this problem is 2 times negative x squared minus 4 times negative x. Now what we're checking to see is if this is A, exactly the same as the original function, or B, if it's exactly the opposite of the original function. Now let's take a look and see what happens. Negative x squared is the same as positive x squared because squaring a function keeps it positive. So this is the same as positive 2x squared. However, negative 4 times negative x becomes plus 4x. Now, because this is not exactly the same as the original function, it's not even. So even is out. It's also not odd because negative f of x, the odd function, this would be if you took every term in the original function and changed its sign. It would be negative 2x squared plus 4x. We have the plus 4x. We do not have the negative 2x squared. So the answer here is that it's neither even nor odd. I'm just going to say neither. Let's take a look at number 3. Now, number 3 is a good example of one that you can tell right away before we even start the problem. I'm going to tell you this is an odd function. And the way I know that is because the degrees of both of the x's are odd. And you'll see exactly what happens in a minute. F of negative x in this problem is negative 3 times negative x to the third power minus 2 times negative x. And again, what we have to do is simplify this. Negative x to the third power is going to be negative x to the third, which cancels out the negative in front of 3 and leaves you with 3x to the third, positive. The odd number of exponents gives you an odd result when you're all done. The same thing is true about the next term. Negative 2 times negative x is plus 2x. Now, if you're following along right now, you'll notice this is exactly the opposite of that of the original function. Negative f of x, in this case, would be positive 3x to the third plus 2x, which is exactly what we have. This is an odd function. Looking at number 4, square root of x plus 1. Interesting choice. F of negative x equals the square root of negative x plus 1. Well, again, this one is, it's going to be a neither. I mean, let's think about this. It's not the original function. There's really nothing we can simplify here. So this is not the same as the original function, so it's not even. It's also not the same as the opposite. Negative f of x in this problem is negative square root of x plus 1. It's not that either, so it's not odd. So this is, again, neither. Now, normally, if we had the ability to graph these functions, which I suppose you could do if you wanted to use calculator cam down below, you totally could do that if you had a calculator for this. But again, we're practicing for the idea that in calculus, oftentimes we're not allowed to use a calculator or we don't need one. So if you did have a graphing calculator, you could just graph these functions and see if they have that y-axis symmetry or rotational symmetry. But let's take a look at f of x equals x squared plus 1. This is a good example of a function that's going to be even, and I can tell you why right now. It's because the x squared is the only term with a variable, and a negative x squared is the same as positive x squared. We'll demonstrate that right now. If you plug in negative x, you get the square root of negative x squared plus 1. Negative x times negative x is the same as positive x squared, so this is equal to the square root of x squared plus 1, which is exactly the same as the original function. And that means that this is an even function. And you know, just because I have the calculator right here, let's graph it really fast, and I'll show you exactly what's going on here. X squared plus 1. If we graph this on our standard window, you'll notice that it does, in fact, have y-axis symmetry. It's an even function. Let's go to the next example here. Question 6, absolute value of 8x. This is another one that's going to be an even function. I'll tell you why in a minute. First of all, if you know absolute value functions, like from topic C, where we graphed an absolute value function, they are symmetric to the y-axis as long as you don't move it to the left or to the right. So this would be the absolute value of 8 times negative x, like that, which is the absolute value of negative 8x, which is the same as the absolute value of positive 8x. These are the same function. Any xy pair that satisfies the first will also satisfy the second. So this is an even function. Now, to go any further now, we need to talk about some other stuff here, because in questions 7 through 12, we are asked to talk about whether these equations are symmetric to the x-axis, y-axis, or to the origin. So we got to do a couple extra explanations before we go. I think this is the end of this topic, though. Yes, it is. Okay, great. We've already kind of talked about the y-axis and the origin, but let's review really quick. We're going to think about this in a little different way. Y-axis symmetry. If xy works on the graph, then negative xy also works. For origin symmetry, sometimes called 180-degree rotational symmetry, if xy works, then negative x, negative y works. And for x-axis symmetry, if xy is on the original graph, then x negative y is also on the graph. Again, imagine a graph that has x-axis symmetry, like, I don't know, this parabola here, this sideways parabola, something like that. This point right there, if we call that xy, then this point down here has the same x coordinate, but the negative y coordinate. So what we're going to do in these problems is we're going to plug in different things. We're going to plug in negative x and y, negative x negative y, and x negative y. And we're going to see if they come out to be the same as the original equation. Let's try that right now with, for example, number 7. So let's try plugging in x negative y. This would test, well, let's label these really quick. Let's start by testing for y-axis symmetry. Y-axis symmetry would be if you had negative x and then a y. This one does not have a y in it, so this would give us 4 times negative x equals 1, which is negative 4x equals 1, which is not the same as the original equation, so it's out. Let's try x negative y. This would be the test for x-axis symmetry. This would give us 4x equals 1, which is exactly the same. So this one totally works. This is x-axis symmetry. And then finally, let's try negative x negative y, which we might start to realize the same patterns going on. Since y is not a problem here, this, again, is not the same as the original equation, so this one's out too. So x-axis symmetry is the only one that works here. Let's try something a little more abstract. These are called implicit functions, by the way. We'll talk about these a lot in calculus. An implicit function just means that x and y, it's not defined as y equals a thing or x equals a thing. It's got equations on both sides. So we're going to play the same game, though. Let's plug in negative x and y to check for y-axis symmetry first. This would give us y squared equals 2 times negative x to the 4th power plus 6, which, if you do the simplification, gives you the original equation. So this works. Y-axis checks out. Let's check x-axis next, which would be x negative y. In this case, we would get negative y squared equals 2x to the 4th plus 6, which again is the same as the original equation. It's because of the even exponents that are going on there. So again, x-axis symmetry totally works. And I believe the third one also works. Because if you since we just tested both those, since it has x-axis and y-axis symmetry, it then also will have rotational symmetry. If you plug in negative x, negative y, the same thing happens again. You get negative y squared equals 2 times negative x to the 4th plus 6, and this gives you the original equation back. Y squared equals 2x to the 4th plus 6. So it's got origin symmetry also. It has all three. These are tough to graph because you have to do some algebraic manipulation. If you're using Desmos, though, you can totally open up a Desmos window and graph this, and you'll see exactly that pattern. Now, you start to get a feel for what's going to happen here, because as it turns out, it's all about the exponents that you have. Like, I can tell you right now that if I change x to a negative, it's going to stay the same. But if I change y to a negative, it's not going to stay the same. So let's think about, for example, x negative y. This would be the let's start with the x-axis. Negative x, y. This is going to work. You can tell that right now, because we'll get 3 times negative x squared equals 4y to the 3rd. That's the original equation. So this has y-axis symmetry. But it will not have x-axis symmetry. Because as soon as you change the y, like if you test to see if x negative y works, it doesn't. You get 3x squared equals 4 times negative y to the 3rd. And because of the odd exponent there, it's 3x squared equals negative 4y to the 3rd, and that's not going to work. This one's out. It's got to be exactly the same as the original equation. And I think since both of them don't work, we can rule out origin symmetry right now and just not worry about it. I'm trying to give an example of where origin symmetry works where they don't both work on this one. I just watched somebody yeet a tennis ball on top of the building from where I'm sitting right now. Let's talk about number 10. We'll go down to the bottom here. We get some other interesting things to look at. X equals the absolute value of y. Again, you can start to see what's going to happen here. Like, for example, let's plug in negative x, I keep doing this the wrong order. Let's start with negative xy for x-axis symmetry. This would give us negative x equals the absolute value of y, which is not the same equation, and therefore it doesn't work. But if we test for x-axis symmetry, x negative y, we have x equals the absolute value of negative y, which is the same as x equals the absolute value of y. This one totally works, x-axis symmetry. But because we've already determined that they both don't work, then origin symmetry is going to be out. on this one. Let's try number 11. Ooh, this one's going to work for all three. I think you can tell that right now. If you change x or y to a negative, it just immediately becomes positive because of the absolute values. I mean, we could write all this out if you wanted to. This would be x negative y. For x-axis symmetry, would be the absolute value of x equals the absolute value of negative y. Negative xy for y-axis symmetry would give you the absolute value of negative x equals the absolute value of y. Or you can even try the origin symmetry. All three of these give you the exact same answer. Is the absolute values take care of it. It's the same as the absolute value of x equals absolute value of y. These all work. All. And then finally we have one more of these. We have number 12, which is probably the most interesting one. If we check for negative xy, for y-axis symmetry, this will work because of the same reason it did in the last problem. Again, the right side of the equation is unaffected, so it's still the same. On the left side, absolute value of negative x is x. So this is the same as the original equation. So this has y-axis symmetry. If we check for x-axis, though, I think you'll see that it does not work. The x is unaffected, but the y's, negative y squared is the same as positive y squared, but this one changes. This becomes negative 2y right there. That will cause a problem. It's not exactly the same, and so therefore it's not going to be symmetric to the x-axis. It's the negative 2y that causes the problem. So this one, unfortunately, is out. And because of that, we can go ahead and rule out the origin right now, because since we know that the negative y doesn't work, we know that negative x, negative y doesn't work also. So it's got y-axis symmetry and nothing else. And there you go. You know, if you had some time right now and you had a Desmos window open, you could graph these and see the actual symmetry develop. But we did this. Oh, wow. Oh, okay. Never mind. We did this from an entirely analytical perspective. So again, I'll give you a minute to kind of just like pause on these and take a look if you want to. This, I'm going to say the same thing at the end here that I said at the beginning. This topic is not necessary for calculus. It does help to be aware of it. We will call on it from time to time. Symmetry can help you find shortcuts for different problems, and that's usually a pretty good thing. Same thing here, even in odd functions, same kind of game. It's helpful to know them and recognize them when they happen, but not super duper necessary. We won't spend a ton of time on them, so there you go. Hey, I hope you enjoyed this video. Again, really proud of you for choosing to take the class. You're going to do great, and I will see you in the next video. Hope you're enjoying your summer.